Okay, so we have a matrix A. This matrix is going to be M by, I don't know, K. Okay, and then you have a matrix B. What do the dimensions of B have to be in order for this product to be defined? Okay, is the product of matrices always defined? So please remind me so we can move on. So presumably I multiply these two matrices and out comes a third matrix. It will have some dimensions. Okay, so by dimensions again of a matrix, we mean a pair of numbers. The size of a matrix or the dimensions of the matrix is a pair of numbers where the first of the pair stands for the number of rows in the matrix, and the second of the pair of numbers stands for the number of columns in the matrix. So for example, AM by K means that matrix A has M rows and K columns. That's by convention. Example, A, this A, first A here, is 2 by 3, has 2 rows and 3 columns, and so on. Okay, so what do the dimensions of B have to be in order for the product to be defined?
Could say K by N.
K by anything, like N, for example. The main point here is that K, which is the number of columns in A, has to be the same as this K here, number of rows in B. Okay, so that's what we talked about last time. And the dimensions of the matrix that comes out on the other side as a result of multiplying these two matrices is going to be M by N, right? Okay, one more thing real quick. Here in this slide, we see exactly how the multiplication is carried out, how to compute each one of these M times N entries. Okay, so here's the resulting matrix here, because I'm multiplying it 2 by 3 by 3 by 2, okay, is going to be a 2 by 2 matrix, C, okay? So it will have these 4 entries, 2 by 2, and each of those 2 times 2 entries is computed in a particular way. The way to compute these entries was what we talked about, dot product of vectors. A vector is the generic term that we use to refer to either rows or columns, okay, of the matrix. So you have a column vector would be this vector. So the first column vector of B would be the column 1, 7, 8. The first row vector of A will be this row here, 1, 0, 3. And their product goes as this entry here, C11 entry by convention. We talked about ways of enumerating those entries. So C11 is the entry in the matrix C that stands, that is placed in the first row in the first column, and that is computed as the product of the first row of A times the first column of B. So that's 1 times 1 plus 0 times 7 plus 3 times 8, and that works out, I think, to 25. So that's the C11 entry of matrix C, and each entry is computed that way. Okay, so just to give a general expression for computing the ijth entry in this matrix C, you just simply take the entries, all of these entries in the ith row of A, and multiply each of those entries. Q is just simply an index that runs from 1 up to K. And again, K is the number of columns in A. Okay, so you take so these entries here are the jth column, the entries in the jth column of B. These entries are the entries in the jth row of B, and so on. Okay, so that's that. Now, what we'd like to do is implement matrix multiplication. Okay, so this is clear, right? This formula, call it formula if you'd like, or expression. Okay, it's clear, right? So we all can multiply matrices, right? What did we note about the product of two matrices last time? Is it what is a commutative operation in algebra? What do we mean when we use the phrase commutative operation? So for example,
AB is equal to BA.
Yes, so for example, if A and B stand for some numbers, real, complex, whatever, then their product, the order in which you place them to compute the actual product, does not really matter. when you're dealing with the field of matrices, is it true that A times B equals B times A?
Not always.
Not always. It may not even be defined, right? So in this case, for example, A times B is perfectly well defined. It's a 2 by 2 matrix C, but B times A is not even defined. Even in the case where, in general, if A is an n by n matrix and B has the same dimensions, n by n, then out comes a matrix that is n by n. This is just the special case of this expression here, when k and m, so this is a special case when m and k and n are all the same number. Okay, these are all n by n matrices. Then in that special case, you're multiplying square matrices by one another, and out comes the square matrix, which has the same dimension as either one of the terms in the product here. Okay, so in this case, A times B is defined. B times A is also defined, but the product B times A does not necessarily equal to A times B. Okay, so it's a good quiz question. Would be give a simple example of a matrix, like let's say 2 by 1 matrix or 1 by 2 matrix, whatever you'd like. That okay, so well, actually 2 by 2. Let's say with the square matrices. Give the simplest example you can think of when the product of the matrices produces a result which is different from the result you would get if you took the product of the same two matrices in a different order. Okay, so I'll let you think about this. Maybe we'll come across an example like this, but that would be really my question to you, rather. Okay, just think of an example. All right, so this is all a review from last time. Now we'd like to implement this operation here in code and look at its complexity. That's our goal today. Okay, so this is what we started last time. This is the, okay, so matrix multiply procedure, and somehow we didn't finish. So now what we'll do now is we'll just finish it now. So okay, so let's again, let me just paste this. Oops. All right, it's not working. Let me paste. Ideally, we wouldn't. Okay, so copy this. That's just simply the formula. Okay, so let's keep that aside. And let's also keep the dimensions of the matrices that we are dealing with. Let A be an M by K matrix, and B be K by N matrix, so that the result that we get is an M by N matrix. Okay, so what are the inputs to this matrix multiply procedure? Okay, so we're going to have A and B are going to be matrices, right? Okay, of these dimensions here, just saving some space here. Okay, that way A and B are matrices of those dimensions there. And out should come an M by N matrix. So what we're essentially doing is we're computing every entry in every M times N entry of matrix C. Okay, so we're going to have a little for loop. And this is going to be a bunch of nested for loops. In fact, I'm going to have 3 nested for loops. And my index I is going to range through the rows of A. So I'm going to have I range from 1 up to M. Okay. And every time I have a row fixed, say I is like 20, okay, one of those rows, I'm taking that row and multiplying by the column of B. So for a fixed I, I'm ranging now through, let's use J for that. This is pretty standard, to N, right? This is the column of B. And how many times do I have to do this? Well, I have to compute each one of the Cij entries. So first, let's set the Cij to 0, because we'll be summing these up. And for this index Q that will range from 1 up to K, right? What do I need to do? I have to update C sub ij. C sub ij, and all I'm doing here is translating this formula that we already know very well about into code. So I'm updating C sub ij, whatever C sub ij was, plus the product of that I qth entry in A, plus the q jth entry in B, in the column, right? Does this make sense? And then once this crunches through, you return, here, you return all the entries, Cij entries. So let's, by shorthand, write down return C. This then simply just return the whole matrix. Okay, so this is nothing other than translating this formula here into code. That's all there is. That's all it is. Now the question is, what's the time complexity of this? What do we mean by time complexity? How long does it take to run? Okay, and how do we measure it in terms of what? So we've seen a couple of examples, a few examples from last time. So we had this linear search, binary search, and there we accounted for the time complexity of those algorithms by measuring, or counting rather, the number of comparison operations that were involved in completing those procedures. So the number of comparisons is what we counted. Here, let's account for the number of arithmetic operations that are involved in this. Okay, well, so we're ignoring, again, as before, these assignment statements here. We're also ignoring, by the way, the increment operator. This is an arithmetic operation. As you run the for loop, you increment I each time. When I runs from 1 to m, okay, at the end of the for loop, you increment I to run the next iteration of 4. We ignore those also. All we account for is simply the number of, well, additions and multiplications. Let's go with multiplications only. How many multiplications do I have here? I'm multiplying, so here's the picture. So I'm computing every Cij that I'm computing. In this picture here, I'm computing C22. I'm taking, these guys. Here's the formula again, same formula as this one, right? How many multiplications do I have? If they're n by n, suppose A is n by n, and B is, didn't have to be, but square matrices, let's say 2 by 2. By the way, when you multiply square matrices, right, so out comes a square matrix. These are the shapes. Okay. In the example, when we had a laid down matrix multiplied by a standing up matrix, what was the shape of this matrix? What's the shape? It's a 2 by 20 million multiplied by 20 million by 2 matrix. So this is 20 million, let's say 20 by 2. I'm sorry, that's the other one. This is, let's say, 2 by 20 multiplied 20 by 2. What's the shape of the matrix that comes out?
2 by 2.
It's a 2 by 2 matrix. That's the matrix multiplication. When a laid down matrix is multiplied by a standing up matrix. Here's another example. How about a standing up matrix is multiplied by a laid down matrix? What's the shape of that? So now you have 20 by 2 multiplied by 2 by 20. What's the shape?
20 by 20.
Yes, 20 by 20. The shape is like that. So these shapes are something to keep in mind. So the first thing you ask, well, like this will, all these matrix multiplication stuff will come back to us when we deal with linear algebra later in the course. So it's a good idea to get a good hang of this now. Okay, I know that you know. I mean, I know that you can look at the formula and sort of like you get it, but let's still, nevertheless, it's a good idea to practice this with, even if you think that you've grokked it completely, still good idea to practice this a little bit. Okay, so these are the shapes. So if you have square matrices, okay, n by n times n by n, you're out. What comes out is an n by n matrix. Okay, fine. The reason I mentioned this Okay, so we'll go back to the question. How many products do I have if this is an n by n times n by n? How many products do I have?
Is it n cubed?
No, just here. Okay, so we'll get back to your answer. That's correct, but it's an answer to a different question. All I'm asking at this point is to compute just a single entry of this. Okay, you're correct Okay, I'll get back to your answer. It's correct but it's an
Yes,
answer
you'll do 2 multiplications and 1 addition.
Yes, for every two two multiplications, you have 1 addition. That's not quite that. Yeah. So if it's a 2 by 2 matrix, if it's so, I don't know if this is what you're. So if you have a 2 by 2 matrix multiplied by 2 by 2 matrix, out comes a 2 by 2 matrix, and each entry here has 2 multiplications and 1 addition. So I'm multiplying 2 numbers and adding them up. Which numbers am I multiplying? These guys. Okay, just to compute this entry, I've added these guys up. These guys up. I'm running out of colors, but you get the idea. Okay, so I've multiplied, I have 2 multiplications and 1 addition. Okay, if it's an n by n matrix, I don't mean to belabor this point. I mean, it's like it's split. I have n minus 1 multiplications, n minus 1 additions, and n multiplications. People see this, right? It's just simply okay. So I don't mean to split hairs here, but the number of additions here is n minus 1. Okay, if it's an n by n matrix, you have n products, and you have in between you have n minus 1 additions stuck there. So for example, in this 2 by 2 case, to compute a single entry, you just need 1 addition and 2 multiplications. Are we on the same page? Right, everyone's on the same page. So 2 multiplications for a 2 by 2 product. So if we account, so why do we need all of this? We want to account for the complexity of this procedure in terms of the number of multiplications. And the number of multiplications that I have, number of mults that I have, the number of multiplications that I have is, help me out. How many multiplications? I mean, Q ranges from 1 to K, and I'm multiplying. I'm ignoring the additions here. So I have K multiplications, right?
2K?
No,
sorry.
it's just K, just simply K, right?
Yeah.
Do people see this? Just simply 1 to K, it's just simply K. Q ranges from 1 to K, and I'm multiplying it for each Q. I'm adding up those. I'm ignoring the sums. So I could be asking what's the total number of additions and multiplications. Yeah, then including this addition, it's going to be that's the 1 addition here, and then the number of additions inside here, that's going to be n minus 1. So you have it in this code, you would have a total number of additions. It's also going to be n. So just let's account for the number of multiplications just for simplicity. So I have K multiplications here, right? Okay. Now this is happening inside this for loop. So this is happening inside this for loop. Okay, I have that many multiplies. So how many times am I doing that many multiplications is the question.
N times.
Sorry, one more time. That's my volume was down. I didn't hear it. Now it's better. So can you say it one more time?
Would it be m times n times?
Yeah, m times n. You know, every time you have I fixed, j ranges from 1 to n. And I then, so j ranges from I to n for every fixed I. And then I itself ranges from I to m. So it's m times n. So, conclusion. So, total number of multiplications is m times n times k. Do people agree? Okay, so the complexity, time complexity in terms of the number of multiplications is m times n times k. Now, special case when A is n by n, B is n by n, then out comes a matrix that is n by n also. So to multiply n by n square matrices, time complexity is what? So all these numbers, m, n, and k, they're all n.
N cubed.
Yeah, n cubed, number of mults is n cubed. Okay, so to give a big O, in fact, it's a big theta estimate. So it's big theta. Let's keep using big O. So it's a big O of n squared operation. Big O of n squared operation. I'm sorry, big O of n cubed operation. Matrix multiply, because each of the n squared entries takes me n multiplications to compute. So it's n squared times n, you simply put. So big O of n cubed. Now, I should tell you that there are faster algorithms. There's something called Strassen's algorithm. That in that Bible of algorithms there, Corman's huge brick of a textbook, it's explained there. It's like, I think it's n to like 2.6-ish or something like that. Maybe some improvement there, 2.5 something these days, who knows. But this straightforward algorithm here that we've just written, that's an n cubed algorithm. So matrix multiplication is n cubed.
Excuse me, can you just say why it's n cubed one more time?
Why is n cubed? Can someone help me explain this? Why is n cubed? So you have,
It's only in the
Let's
special
take-
case that you're multiplying.
yeah. That's correct. That's correct. But let's just verbally explain, not just simply saying that, I'm just agreeing with you that matrix multiplication in the general case is this, and now let's plug n for each one, and we'll end up n cubed. That's okay. That's an explanation. But then you kind of have to buy our whole previous argument. So why it's n times k. So let's argue this verbally in a couple of sentences. Can anyone, starting from the following? You're multiplying two matrices, A and B, each of which is an n by n matrix. So I'm multiplying two square matrices, A and B, with dimensions n squared each. Can someone in just two sentences only, at most, give a compelling reason that the product, to compute the product of these two matrices, I would need roughly big O of n cubed time? Can somebody say it in like no more than 3 sentences, let's say, but clearly, so that everyone who's willing to parse those sentences mentally now, without writing anything down, will agree with you. Can anyone say this?
I can try.
Yes.
So the resulting matrix is going to be an n by n, right? So then that means there are n, obviously, in the column and in the row. Now for each one of those, we have to multiply like 2, or we have to multiply, I guess, n times for each one of those entries.
Mhm.
And that totals up to n by n by n.
Yeah, that's exactly right. Are people agreeing with this? I'm just trying to write down shorthand what you just explained, so that people have a chance to agree or disagree, for that matter. It's always good to disagree, but it's hard to disagree with this reason, right? Is everyone on the same page? So I'm multiplying an n by n matrix by an n by n matrix, and just simply repeating what you said. The result, I know, is going to be an n by n matrix. So that result has n squared entries. Each of those n squared entries took me n multiplications to compute, for a total of n squared times n multiplications. N squared times n is otherwise known as n cubed. End of argument. Does that make sense? Are we all on the same page? Okay, great. So that's great. That was exactly a great explanation, the way you've given us your explanation. Okay, now, so we've just written down this algorithm there. Okay, so we have Oh no. Oh no. I don't have an example. Okay. So let me bring an example. This happened in the other section too, but I have an example from the other section, which is what we'll use. Now I'd like to draw your attention to something. I want to do an example. We're not done with matrix multiplication. This is the kind of example I'm going to do now that may show up on the quiz. Very likely will show up on the quiz. So here's the question. Okay, we're good with matrix multiplication. We're kind of buying the idea that it's n cubed. When you read again your text, you will be more convinced of this. So if there's something you feel uneasy about, you should definitely reread this. And it's normal to feel uneasy if you're seeing this for the first time, especially. So here's your matrix A. Let's say it's a 3 by 2 matrix. Okay. So let me get this exact same example so that all sections are on the same page. 1, 0, 2, 3, 3, 1. So my A is a 3 by 2 matrix. Then I have a matrix B, which is going to be a 2 by 4 matrix. So this matrix is lying down now. 1, 2, 1, 2, 1, 0, 0, 1, 0, 2. Okay, so that's my second matrix. Third matrix is this one is like 4 by 1 matrix. It's a 4 by 1 matrix. It's going to be 1, 1, 0, 1. So here's the question. So here's something I want to tell you something. It's more of a, if you've taken linear algebra, you've seen this. Although matrix multiplication is not a commutative operation, okay, so again, A times B is not B times A, so I mean, it is an associative operation. By this, I mean that, now I'm assuming for a second that all these products that I'm about to write down are defined. By this, I mean that A times B, if I take A times B and look at the result of what A times B is, and I take that and multiply it by C, what I get on the other side, the result of this computation, is the same as if I were to take B times C first and computed that, and then multiplied that from the left by A. This is called, now I haven't proven this to you, and this is something proven in linear algebra. And we'll verify this, the fact that this associativity holds with this small example here. But there's a little bit more that we want to do with this example. Now, this, although I'm not proving this now, and that's not a difficult proof, it's just tedious. You just work with the definition of matrix products. It's not super exciting, so nobody likes to do this kind of proof. But if you're taking linear algebra, it's the sort of thing you have to do once and leave it aside, and you don't care about it. You know that this is true and it works. So this is true. What this means is that I can drop the parentheses altogether. If no matter where I place these two parentheses, the result is going to be the same, then I just simply say I'm not using the parentheses at all. And when I write down A times B times C, there's no ambiguity as to what that means. That can only mean one thing. The result is the same no matter where you place the parentheses. So people usually drop the parentheses in matrix multiplication sometimes, right? Because it's not ambiguous what it means, what the result is. Now, here's that more that we want to do here. What I want to do is I want to compute. Now this is so mathematically, this is the same result, which we'll verify in a second. However, it turns out that computationally, it makes a difference the way you compute these products. Okay, so let's see how exactly. So let's compute this product the first way. So let's call this the first way of computing, and let's call this the second way of computing. Okay, so the second way of computing the same exact product. This is the second way. So let's start with the first way. The first way of computing is going to be to compute A times B first. Okay, so this is part A of 1, and then part B is going to be whatever result I get there when I compute A times B. I'm going to multiply that by C. Okay, this result. Let's compute A times B. First of all, I have a tall matrix multiplied by a laying down matrix. What will be, what kind of, so let me rewrite this. Okay, let's take this one. So this is A. That goes here. So I'm multiplying this matrix here by a matrix that is laying down. Okay, so let's just multiply them. Okay, so somebody help me. How many entries? Sorry?
It will be tall, the result. It will be 3 by 4.
It will be 3 by 4. So I will have 12 entries. So let's compute this first entry. And by the way, I'm going to go here, so I know that you know how to compute these now, and you'll help me just to reinforce what you already know. But there, looking ahead to linear algebra, I want to, have people pay attention to a couple of things also. So I'm going to do this. Well, we're going to do this a little bit slowly, and we're going to have a little bit scratch work here also on the side that I will be erasing. But please, let's do it together. So here's what we have. What is the first? Okay, let's compute. So I'm going to have 12 entries. The first, each of these rows will have 4 entries. So what's this first entry here? It's going to be 1 times 1 plus 0 times 0. Agreed? So it's going to be 1, this entry. Good? What's going to be the second entry? It's going to be 1 time, yes, 1 times 0 plus 0 times 1. So it's going to be 2. I have this entry here. It's going to be 1 times 1 plus 0 times 0. That's going to be 1. And the last entry is going to be 1 times 0 plus 0 times 2. And that's going to be 1. Now notice what happened here. Here's the scratch work.
That's going to be 0, not 1.
That's going to be 0, yeah. That's going to be 0, of course. That's going to be 0. So what I have is I took the first row of the matrix and multiplied it by the whole matrix here. And out came, of course, the row. And this row was 1 times the first row, 1, 2, 1, 0. And notice that I'm kind of like doing, when I multiply 1 times the row, it's a scalar, some number. By a scalar, I just mean a number. Number times a different kind of entity, a vector, right? Plus 0 times this entity vector. And how do I multiply a scalar by a vector? I multiply each individual component of that vector, of that row, by that scalar itself. Okay, 0, 1, 0, 2. And when I added those two up, I got, 1, 2, 1, 0, which is what ended up here. So this is like, may look obvious to you and not quite clear why am I saying this? But the point I'm trying to make here is that you can take a row and multiply it from the left by a matrix. And what that amounts to is taking each row of the matrix on the right-hand side and weighing it by those scalars that sit in the row that is on the left-hand side. Did this make sense, just what I said? So here, when I multiplied the row by the entire matrix here, what came out was a row, first of all. So the first thing you do every time you multiply matrices, before you even do any computations, what's the dimensions of the resulting matrix? So I knew it was going to be just one row of length 4 that came out on the other side. But how did I get that? I got it by weighing, like multiplying 1 times the first row plus 0 times the second row. If I had the third entry here, I needed the third row here. Okay, so I would multiply 1 times the first row plus 0 times the second row plus whatever that number was times the third row and so on. This is called linear combination of rows. By linear combination, this is looking ahead. By linear combination, we mean of vectors, in this case, row vectors. We mean take the first row multiplied by some number. Take the second row multiplied by some other number. Take the third row multiplied by the third number and add them up. This is called a linear combination of vectors. Now this, the last 5-10 minutes of our discussion was the complete aside, but something that I want people to keep in mind, because these considerations will be material to us in the linear algebra section. For now, if you're just multiplying these things, okay, so we're multiplying these things. So let's continue. We're not done with computing the product of these two matrices. This is what we're computing. So what's this entry here? Again, we're going to have a total of 12 entries. Okay, this is quite quick to compute. So let's compute the second. So notice what I'm doing. I'm taking twice the first row and adding to it 3 times the second row. And of course, each individual entry is computed that way. 2 times 1 plus 3 times 0. That's going to be 2. 2 times 2 plus 3 times 1. That's going to be 7. 2 times 1 plus 3 times 0. That's going to be 2. And so on. 2 times 0 plus 3 times 2. That's going to be 6. Okay. So this row, again, as an aside, this row, this entire row, how did I get it? I got it as a linear combination of these rows. What are the coefficients in the linear combination? That is the weights by which I'm weighing up these rows. 2 and 3. I got this row by taking 2 times this row plus 3 times that row, and that was my result. Now to compute my third row, the last row in the final result, I need to weigh 3 times this first row and add to it 1 times the second row. Let's see what it works out to. 3 times 1, 3 times 1 plus 1 times 0. That's 3. 3 times 2 plus 1 times 1. That's 7. 3 times 1 plus 1 times 0. That's 3. And finally, 3 times 0 plus 1 times 2. That's going to be 2. And that's my answer. It didn't take that long to compute this matrix, right? But I did have to compute 3 times 4 entries. Each of these 3 times 4 entries, I will be asking in a minute, how many multiplications did I have to carry out to compute each one of these 3 times 4 entries? Okay, but back to our one level up. We are still after this product. A times B times C is what we need to compute. So let's continue. So now I have, so here I had like 3 by 2 matrix multiplied by 2 by 4 matrix. So out came 3 by 4 matrix. Good. Now I'm taking this 3 by 4 matrix and multiplying that by a 4 by 1 matrix. Okay, so what's that result? Okay, so let's take that.
3 by 1.
3 by 1. Exactly. So let me copy that. And let me paste that. That's our matrix 1. Okay, that's our matrix 1. And then I'm going to take this C, and out will come, as you've just told us, a 3 by 1 matrix. So let's compute that. 1 times 1 plus 2 times 1 plus 1 times 0 plus 0 times 1. That's going to be 3. Agreed? What's going to be 2 times 1 plus 7 times 1 plus 2 times 0 plus 6 times 1? That's 2 and 7, that's 9 and 6, right? 15, right? That's going to be 15. Finally, what's going to be 3 times 1 plus 7 times 1 plus 3 times 0 plus 2 times 1? That's 2 and 7 and 3, that's 12. That's 12. So that's the answer. Okay, now I have a second way of computing the same result. The second way is going to be multiplying B times C first. That would be my first step. And then the second step is going to be taking A and multiplying that by the result. Okay, so B times C, let's multiply those. Here's my B. That's my B. Okay, so let's actually make sure we separate these guys here. Okay, so that's my B, and my C is going to be this guy. So I'm multiplying these guys. Okay, what's the result? First of all, what's the first thing that I'm asking here? I have a 2 by 4 matrix multiplied by a 4 by 1 matrix. What comes out on the other side?
2 by 1.
2 by 1, right? So what are the entries in this 2 by 1? What are the, so help me out. I just want to make sure that I'm not the only one speaking here, that we're all on the same page and you're following along, making notes and also computing with me.
The first element is 3.
Okay, yeah, so 1 times 1 plus 2 times 1 plus 1 times 0 plus 0 times 1. That's exactly 3.
Yes, and the next is 3 as well.
And the next works out also to 3 because it's 0 times 1 plus 1 times 1 plus 0 times 0 plus 2 times 1. And when you add those up, you end up with 3. So you have this 2 by 1 matrix that comes out on the other side. It's 3, 3 column vector. Just 2 entries. Okay, so now what I'd like to do is multiply my A by this result, 2 by 1 vector, which is 3, 3. So let's see what we get. So let me take my A. Here's my A. Just copy. I'm going to paste this. So that's my A. And we want to multiply this by our 3, 3. So this was 3 by 2 multiplied by a 2 by 1. What's the dimensions of the matrix that come out on the other side?
3 by 1.
3 by 1, exactly. What's going to be the result? 1 times 3 plus 0 times 3. That's 3. Two times 3 plus 3 times 3. 2 times 3, 6 plus 3 times 3, 9. That's 15, right? So help me out. 3 times 3 plus 1 times 3. I have no idea what that is. What is that?
Well,
I think that's 12. I think I agree with you. Okay, so that's going to be 12. So that's the answer. That's the answer. That's the answer. And although I haven't proven to you the associativity of matrix multiplication in the general case, in this particular example, I think it's clear to us that this is the same as this answer. Okay? Okay? So either way you multiply these matrices, you get the same result. However, the question is, how about the effort involved in these two different ways of multiplying matrices? Let's account for that. Okay, so how many multiplications did I use in the first case? Number of mults.
It's 36.
Oh, yeah, yes, it is 36. But let's be completely clear so that everyone's on the same, reading from the same sheet of music, right? To compute each one of these 12 entries, here I have 12 entries here. How many multiplications did I use? 2, right? Because I 1 times 1 plus 0 times 0. That's 1 times 1 plus 0 times 0. 2 multiplications. Each one, that's 6. How did I compute this 6? How did I compute this 6? How many multiplications did I use to compute that 6? 2 times 0 plus 3 times 2. That's that 6. That was 2 multiplications. So every entry in this 3 by 4 matrix took 2 multiplications. For that many multiplications, number of mults. But then I wasn't done. I had to compute more. I had to find this final answer. This final answer had 3 times 1 entries, was a 3 by 1 vector. And to compute each one of those entries, it took me how many multiplications? This times that, plus this times that, plus this times that, plus this
4.
times that. How many?
4.
4. So that is the number of multiplications in the second step. When I added those 2 up, the first one is 24. The second one is 12. So the total is 36, as you've just told us. But how about the second way of computing the matrices, the product? How many entries do I have here? 2 times 1, right? How many multiplications did it take me to compute each one of those 2 times 1 entries?
4.
4 multiplications, right? Everyone sees that? This times that, plus this times that, plus this times that, with 4 multiplications. To that, once I've carried out that many multiplications, 2 times 1 times 4 multiplications, I had to carry out another 3 times 1 multiplications here. 3 times 1 vector. Each one of these 3 times 1 entries I computed by doing how many multiplications?
2.
2 multiplications. Okay. For a total of 8 plus 6, which is 14 multiplications. So the effort, apparently, in these 2 different ways of computing matrices is 36 versus 14. So clearly, this is preferable, right? Because you're doing fewer multiplications. So apparently, where you place the parentheses in terms of what the final result is does not really matter, of course, but computationally, it makes a huge difference. It matters where you place the parentheses, okay? Because the effort involved is, it's like, sometimes can be a drastic savings of effort. Okay, so if you have like a gazillion, maybe not a gazillion, like, I don't know, even like a modest amount, I don't know, let's say you have 100 matrices to multiply. Okay, and each one is like 1,000 by 1,000 matrix, let's say, which is not unusual. With several thousand by several thousand matrices in data science applications, it's not unusual at all. And if you have to multiply a few of them, it matters where you place those parentheses. And it's another question of where is the optimal way of placing the parentheses. It's a good question to think about. It's a combinatorial problem for which we now don't have time. Are there any questions about this? Any remarks? Because we need to do a couple of other things to wrap this up. So I also wanted to start talking about induction today, but looks like we may not get there. Any questions about what we've covered? So a question like this, you may say on a quiz, right?
I have a quick question.
Yes, please.
Could you go to the one that you had, like the multiple, like bottom multiply problem one? Which one is that? Just like the last lecture one that you did on the slide. Which one was it? The one where you had, what's it called?
Is it from the previous lecture?
No, it's from this one. It's the one that we just did.
Okay. So here's the second way of computing.
It's the one with the Cij of the equals Ci and J, which is the scratch paper problem. Yeah, that. How did you get I and J into like multiply together, and like where did that came from with that function?
Okay, so I and J. What do you mean I and J multiply? I and J are indices. They're never multiplied together.
Okay, because that's what I was just confused of. How did that get to that situation, or was this originally in that problem from the scratch paper?
Okay, so I just want to make sure, just to be clear. So ij is not a product of anything. Is that clear?
Okay. Yeah, it's they don't call it exponent, but it's like whatever that like number that's like on the bottom of a certain variable.
Yeah, that okay. So just to be clear, so this is not a so ij stands for the ith row and jth column of matrix. This is just to
Okay.
it's just a way of referring to an entry in the matrix. Does that make sense?
Yeah.
So I have a 2 by 2 matrix. This, what we've computed here, this is C11. It does not mean that I'm multiplying 1 by 1, those subsets.
Yeah.
It's just the first row and the first column. Just has to do with indexing the matrix, square matrix itself. Because the matrix is a grid of numbers arranged in a rectangular structure. I have to refer to each element somehow. A convenient scheme for referring to individual elements in a grid would be to say in which row and which column that element is. Does that make sense?
Yeah.
Yeah, so it's
it makes sense.
Okay, so it's a way of referring. So what this says here, that this particular element, which stands in the ith row and jth column, can be computed this way.
Gotcha.
By adding okay.
Yeah.
Right.
Thank you.
Okay. All right. Any other remarks? Questions? Anything? Okay, so now we have to move on. So what is a polynomial? This is a polynomial. A collection of n plus 1 numbers is an n degree polynomial. Okay, strange thing to say, but not so. Let's see how. Here's a polynomial of degree 3. This polynomial of degree 3, okay, so n is 3 here. It's the highest degree, x to the 3, so n is 3. The way you write down the polynomial is writing down by these n plus 1 numbers, like that, where the coefficient a sub k corresponds to it's the coefficient by x's kth degree. So you have x to the degree, so they call it polynomial for p for polynomial in x of the nth degree. Sometimes this is sometimes the notation used, but let's actually not use this notation. So just polynomial. Here's the polynomial. This is the polynomial. It has n plus 1 coefficients. It's a degree n polynomial. Okay, so for example, in this particular case here, this polynomial is a 3rd degree polynomial. So you have a 2x squared here, you have a 1x to the 1st degree, and you have a 0 x to the 0th degree. So we don't write x to the 0th degree. You can write it down if you'd like. That's just 1 always, no matter what x is. Okay, so that's a polynomial. The question is evaluate this guy at some particular point. Okay, 2. If you like seeing these in pictures, if you were to plot 3rd degree polynomial, will look something like that. Okay, and on the R2 plane, that's a 3rd degree polynomial. And the question is, here's x equals 2. What is the value of this polynomial at x equals 2? That's the question. How do you write a computer program that computes the value of this polynomial at that point x equals 2? And here's a computer program that does it. We'll run this through this particular example to make sure the pseudocode makes sense. And then I'll ask you the question of what's the runtime of it. Okay, so let's see how this algorithm works. So initialization step. Init step says the following. This power, some variable power, is initialized to 1. This is the most straightforward way of computing the value of this polynomial. Power is initialized to 1, and y is going to be my answer. Y contains my answer at the end of the day. Initially, it's set to a0, which in our case is 5. Okay, that's the initialization step. This is what I've written down is this step. Now I drop into the for loop, and I have I equals 1 is the first step of the for loop. When I get into the first step of the for loop, my power gets updated to whatever power was times c. What is c? C is where I'm evaluating. Let's give it a different color so that people are on the same page here. Let's go with orange. Okay, so times 2. I'm evaluating this at c equals 2. So power gets that. This is what I just did, this step. And then y gets updated to whatever y was before plus a sub 1, which is 7. Here's a sub 1, 7 plus 7 times power. Okay, 7 times power, which was 2. So 7 times 2 plus 5 looks like this is 19 to me. So that's the first step. Step 2, I equals 2. That's my step 2. Power gets to be 2 times whatever the value of C was. That works out to 4. And then y gets updated to whatever y was before plus a sub I. What's a sub I? Here's a sub 2. 9 times power, 4. 9 times 4, I think that's 36. 36 and 19, that's 56 minus 1. So that's 55. Step 3, that's the last step. Power gets to be 4 times 2. That works out to 8. And y gets updated to 55 plus A3 is 3 times power, which is 8. 3 times 8 is 24. 24 and another 55, that's 79. So that's the answer. So if you plug in 2 into this equation, if you plug in 2 and compute the result, you'll get 79. That's the answer. Our question is, what's the runtime of this guy? It's the runtime. Well, then you ask me how, well, in terms of what? And the answer is in terms of arithmetic operations again. How about the number of, let's go with the number of multiplications again. So I have some addition and multiplication, but let's count it in terms of the number of multiplications. The number of multiplications. How many multiplications am I carrying out?
2n.
Sorry?
2n.
Multiplication is 2n. So what's the big O runtime then? Constant times n. We get to drop constants, a polynomial, linear time. So big O of n.
N.
Big O of n. Now let me ask you this question. Is this an optimal algorithm in terms of big O of n? Can I do any better than linear time? Linear time means dependence on n, the number of coefficients that well, actually I have n plus 1 coefficients, but so about n coefficients. Can I do any faster than this? Can I ever do, let's say, in constant time? I could never do this in constant time, right? Because I have to look at those n plus 1 coefficients. Otherwise, I wouldn't be looking at the polynomial itself. I need to know what the polynomial is, so I need to know every coefficient. So I kind of have to look at n plus 1 elements. So as n grows, the number of elements that I have to look at will also grow. And when I'm computing this value of the polynomial at some point, I've looked at n of them. So that my algorithm scales linearly with n. There's no way I can do better than that. So there's no way to evaluate a polynomial in better than linear time. Do people agree? Right. Now, that's what we agree, and that is all true. But then along comes the guy whose name is Horner, and he says, look, I've got a better way of computing polynomials, evaluating polynomials. And people say, there's no way, you can't do better than big O of n. And Horner says, oh, wait a minute. Well, let me show you my way of computing the polynomial. So let's take a look. Okay, so we're still correct. He can't do better, but he's, it's just a clever guy and wants to do a little better. So he wrote this code down. Let's evaluate the same polynomial. Again, we have, these are our coefficients. Let me copy these guys so that we're doing exact same problem, but slightly differently. So let's run through this procedure. So this is how cleverness, I suppose, pays off. This is quite cute. So initialization step. Y, which again is going to be my answer, is initialized to a sub n. Before we started with a sub 1 and just plugged it, we chugged along. Just this was the previous example was just a straightforward way of doing it. He starts from here. Let me, he says, say that my answer is going to be a sub 3. The answer is 3. And then he goes into the for loop. So he goes into the first step when I equals 1. He says y, notice that he just has one line here. Before, we had 2 lines. He just has one line and does one multiplication inside of it. So y is going to be 3 times c, which is still 2. So just to be clear, c is 2. So x at x equals 2, we're evaluating this thing. So c is 2. Plus, so y gets, I'm inside the for loop, this is what I'm doing, y times c plus a sub n minus 1. What is a sub n minus 1? That's a2, which is 9. So that gets evaluated to 3 times 2 plus 9, that is 15. He's done with step 1, evaluated this 15, goes to step 2, equals 2. All he does here, again, updates y, but in a clever way. Y, he says, is now going to be whatever y was before, multiplied by my c, plus the a sub 1, which is the next a down. Okay, so again, I'm just plugging in the numbers into this line. That works out to be to 37. And then he does the final step. I equals 3. So he updates y one more time. And he says that's 37 times 2 plus 5. And 37 times 2, that's 74, plus another 5, that's 79. So 79 is the answer. And of course, we got the same answer here, 79 there. Either way you go about computing this, you still get, of course, 79, as we did with the matrices. Either way, associativity holds. Either way you compute it, it's going to be the same answer, mathematically, of course. But in the case of matrices, one was clearly better. In the case of these ones, that we just showed that there's no way to do, and we were correct. I mean, the argument we gave holds water big time. It was big O of n. You can't do any better than that. What's the runtime of this, just to make sure? What's the runtime? Okay, this is E, believe it or not. Okay, so what's the runtime? How many multiplications? Number of mults? Sorry? N, right? I'm doing just one multiplication inside. That's all I'm doing, right? If I'm ignoring the additions, assignments, I'm incrementing the for loop, all of that stuff. N multiplications, it's still big O of n. It's still big O of n, just as the previous version. But it's better, right? So I'm doing less work inside the for loop. Instead of 2 multiplications, I'm doing 1. Still big O of n runtime, but so this is nicer. So how did he come up with this? So let's see what was in his mind when he wrote down this rule. How did he, as a kid, he practiced with algebra, right? That's how he was able to write this down. Now let's see what I mean by this exactly. So here you have, let me copy 5 plus 7x, 5 plus 7x plus 9x squared, right? And plus 3x cubed. Can people tell me what he did here? How did he come up with this? What did we compute first? Let me tell you. This is, first of all, this is x cubed here. He computed this, x squared 9 plus 3x. He took that x here, which was 2. 3 times that 2 plus 9. 3 times that 2 plus 9, right? Let me rewrite this so you can see it. Then let me just leave this alone. And then now you can see the following. You see the structure here? What the guy did? Then we computed 7 plus x times 9 plus 3x. Do you see what he did? He started from inside. Computed this. Then he computed this. What's this? That's whatever is inside. 7 plus the result of the previous. 7 plus the result of the previous. You see how clever this is? Okay, then he took that result and computed 5 plus x times the previous. 5 plus x times the previous. The whole thing. 5 plus that. That's this. So he starts from the inside here, then computes that, step 1. This is that. Then this is step 2. Then this is step 3. From the inside out. You see, do people see how clever this is a little bit? It's still big O of n time. I mean, it's just theoretically you can't beat it. So that's true, you can't beat it, but it's much nicer. I don't know if you agree with me that it's nicer or not. I mean, after all, at the end of the day, the niceness of this is quite a subjective experience. It's in the eye of the beholder, so to speak. But I think most people would think that the second way is cuter. Plus, it takes you fewer computations, right? Although they're both linear, we can easily argue, which we did, that you can't really do better than big O of n time, because you have to look at every coefficient. Otherwise, you don't see the polynomial, and you need to compute the value of the polynomial at a given point. So you have to look at every coefficient. I think we have to end here. Are there any questions?